Hello everyone. In the previous video, we have seen one of the adversarial search algorithm called as minimax algorithm. In this video, we are going to see an extension of that algorithm, which is alpha beta pruning. So this is introduced to mitigate the problem which is there in a minimax algorithm. So in minimax, the number of game states it has to examine is exponential in the depth. This is the fundamental problem in minimax algorithm. Number of nodes are in exponential in nature. To reduce that, we have discussed earlier that we can use pruning and various heuristic functions to remove it. So here, let us see how alpha beta pruning technique employs pruning methods to minimize the tree and thereby reduce the number of nodes to be examined. So the solution is it can be reduced to half by computing the correct minimax decision without looking at every node in the game tree. So sometimes some nodes need not be pursued or examined because of the conditions it has. So we will be exploiting that to reduce the number of computations, and this technique is called as alpha beta pruning, where it prunes away branches that cannot possibly influence the final decision. So the general principle in alpha beta pruning goes something like this. Suppose consider a node n somewhere in the tree, so that player has choice of moving to that node. So if you have a node n, and if you have a better node in the parent or in the adjacent parent, then there is no need to pursue that node n going deeper and deeper. So we can prune that particular node n. So it employs alpha beta pruning employs such a technique to minimize the computation. So let us see one example and algorithm to better understand this. For example, consider node A. So here we can see that it's a two-player game, max and min. We have already discussed how the game happens in the previous video. So once first A takes action, if he takes action A1, it reaches to state B, and if B takes action B1, it reaches to the terminal state with utility value as 3. So as we can see here, we have two values which are called as alpha and beta. The alpha stands for the value of the best choice we have found so far at any choice point along the path for max, and beta is the value of best choice we have found so far for any choice point along the path for min. So basically these square brackets here indicates alpha and beta values. So we would try to minimize this range so that we reach to the point where A can take a better final output value. So let us see how this algorithm works. So here currently the terminal state is 3, and initially the alpha and beta values are alpha is equal to minus infinity and beta is equal to infinity. So since there is a terminal state with 3 and minimum value there is only 1, so it can take 3. So the set space has been reduced from minus infinity to minus infinity to 3. And if you go to the next state, 12 is greater than 3, and so minimum player will not choose 12 because you already have a better action which results in terminal state 3. So b2 will not affect. So here next comes the terminal state 8, and this is the final terminal state in under node B. So once the node B the terminal state is 8, and this is once again greater than the previous terminal state, which is 3, and therefore we can say that there is 3 is the better state and b1 is the better action. So this changes our range completely from minus infinity to 3 to 3 to 3, because there is no other possible action which we could result in a better value. So the best possible state value a minimum player can take is 3. So minimum player will always try to reduce the utility value and maximum player always maximize it, but they go in turns. So first here when we see the minimum player has got the value 3, and now if you see the maximum players So it is no more minus infinity to infinity, it is 3 to infinity, because you have a terminal state which results in at least 3 value. So we and maximum value always tries to maximize that, so there is no need of placing it minus infinity. You have a better higher value, which is 3. So the range now it is between 3 comma infinity. So as we move along the tree, this range decreases, the range decreases, so that we reach to a point finally to a one single exact value. So let us see by going forward. If you take the next action for state A, which is A2, that results in state C, and if state C takes the action C1, it results in terminal state 2. So here 2 results in minimum player value. The range reduces from minus infinity to minus infinity to 2, because there is at least we are having a player which we are having a terminal state which is 2. So there is no need to further explore greater than 2, because 2 is, this is the minimum player and he wants the as minimum as possible, and we got 2. It only looks for the values which are less than 2, because there is always a possibility that some other terminal state can give less than 2. So but greater than 2 it is not needed to explore, because it is not useful, because minimum player anyway will ignore. So that is the exact point which we are going to exploit here. So the next 2 states have values of terminal states which are greater than 2, but we are in no need of that value, because it will not change the range of state C from minus infinity to 2. So we'll see with the exact algorithm step by step how it goes later, but broadly here the no terminal state which has values 4 and 6 are not affecting the state C in alpha beta pruning. So next comes node D. So as you can see here, so here node D, when it takes action D1, the range has reduced for D from minus infinity to minus infinity to 14, and once it finds a better value, which is when it takes action D2, the terminal state is 5, so 5 is better than 14 because it reduces the search space, it reduces the range. So 14 is updated to 5 at state D. So in the same way, finally we have state 2, a terminal state with utility value as 2, and that has further reduced the D state value to 2 comma 2. So here, as you can see, in both of the cases, action A2 and A3, they are not, the max player will attempt to maximize the value, and we got 3 as the value, but from state C we got 2, and from state D we got 2. So A2 and A3 actions are not resulting any better state value for A, and A1, the value 3 which we got from action A1 is the one which is going to be finalized. So in this way, without exploring a state, without exploring a region of the tree, we are able to actually conclude the values of state A. So this reduces computations, but this is only a broad overview. We will see step by step with clearly how the algorithm works and what happens at each state. Let's see an example for alpha beta pruning. Here we can see the tree with the same terminal state values which we have seen earlier. So let's see how this algorithm works step by step, so that we implement alpha beta pruning. So as we can see here, we have a alpha beta search function, and this calls max value functions. So, and as we know earlier, it is recursive, but there are 2 functions, max value and min value, and each of them calls one after other. which means max value function calls min value function and min value function calls max value function, and this turns goes on until some function reaches the terminal state, and this whole of these two steps are present in alpha beta search function. So it starts with max value and it takes turn recursively until it reaches to the terminal states. So let us see how this algorithm works step by step. So first I'll be using some shortcodes. Max value I'll represent using mxv, and min value I'll be representing using miv, and alpha beta search using abs. So let us write. So it starts with node a. So abs of state is a. So this function, which is abs of state a, is going to have, first it calls for v is equal to, it calls mxv first function, which is, I'll be writing mx function using red color for easier understanding, mxv, and inside we have state as a, alpha value as minus infinity, and beta value as infinity. So this is the first function which is calling the mxv function with state a, and once you go to the mxv function, here we haven't reached to the terminal state, so there is no need of going to that if condition. It starts with v value, which is equal to minus infinity. So v is equal to minus infinity, and then there is a for loop which takes for each of those actions. So we have a1, a2 and a3 actions. So we are currently doing for action a1. So this is for action a1, the loop is going to run. So in the first action we are going to have v is equal to max, so it calls a maximum value. So max of the v value is minus infinity. So and we are calling the min value. So I'll represent min value using a small miv. So miv of the result of s comma a. So I'll represent result as r for easier convenience. So result as r, and the state is, it was s is here a, and it has taken action a1. Okay, and we have a alpha value as minus infinity and beta value as infinity. So this is what is the first step inside the for loop, inside this function max value. So for that to know, we need to run min value function. So this function we are going to work on. So here once it goes to the min value function, here once again we did not reach terminal state, v value is infinity. So v is infinity here once again, and once again you have a for loop for each of those actions. Here the result of a comma a1 is b, and this b has multiple actions b1, b2, b3. So we'll be starting with b1. So if you take v is equal to min of v value is infinity here, and max value, which is mxv. So let me write in red color. So mxv. So this function here, so here the once again result function. So r of our current state is b, and the action it is going to take is b1, and the alpha value here is with the same values we have got, minus infinity and infinity. So these are the values. So for these particular values, so we need to compute this value. So to compute this value, as you can see here, this is nothing but the terminal state mxv of b comma b1. It results in a terminal state with value as 3. So this v value minimum of infinity comma 3 will be equal to, so v is equal to 3 value. And so now it goes and checks whether v is less than or equal to alpha. So here v, which is equal to 3, this is less than or equal to alpha. Alpha is minus infinity. So you can see it is important to note the alpha and beta values inside the min function and outside the min v function. So here alpha beta values and here alpha beta values will be different. So you will come to know as we move along. So v is equal to 3 and that is less than or equal to alpha. Here alpha, which is equal to minus infinity, but this condition it does not satisfies. So because 3 is not less than minus infinity, so this is wrong. So here we will be going to the next step. So it will not return v value, instead beta value will be computed. So beta is equal to min of beta value earlier is infinity and v value here we got as 3. So this whole thing results in beta is equal to 3. So now alpha and beta values, if you see at this moment inside this loop, so I'll use a different color code to indicate what are the alpha beta values inside. So let me use say different color. So here alpha comma beta values inside the min function is equal to alpha is the same value, which is minus infinity, but beta value got changed to 3. So this is the first iteration we have run. So the next iteration we will be going back. Here in the next iteration v value changes because we got 3 and also beta value also changes. So let us now take, so for the new iteration, so let me just drag this so that to indicate a new iteration. So here v is 3 and also remember that here the beta value is also, because 3 we have got updated. So this is the loop the loop which is there in the min value function we are currently in. So v is equal to 3 and beta is equal to 3. So let us once again write the iteration, go through the iteration. So v is equal to min of v value is 3 and once again we have max value function. So here this max value function mx v will be the result of b comma, this is the second action from b comma b2, and alpha value is same minus infinity, but important thing beta value got changed to 3. So that's it. Now here if you compute this value is nothing but mxv of, this is the terminal state 2l and minimum of 3 comma 2l is 3, so v is equal to 3 and so this is also, so v is equal to 3 which is less than or equal to alpha which is equal to minus infinity. So once again this condition does not satisfy, so we can actually cross this. So our beta value will try to see once again if it can be updated. So here beta will be equal to minimum of, so here beta is previous beta value is 3 and the new v value is 3. So our minimum of 3 comma 3 is 3, so beta is once again 3. So we'll be going to the next iteration. So for the third iteration, so we'll be having v is equal to once again 3 and beta is equal to once again 3. So here we will be having v is equal to min, so this is inside min value function. so it takes little longer, so we need to be careful. So here v value is 3 once again, and once again it calls max value function, so mxv. So this function will have or of third action b comma b3 comma alpha value is minus infinity, and beta value is, alpha value did not change, and beta value is 3. This also did not got changed. So this whole thing will be here, and we already know this value, it will result in a terminal state with value as 8. So min function of 3 comma 8, that which is 3. So v value is 3, and so we have v value as 3, and if you pass through this condition, so v is equal to 3, which is less than or equal to alpha, which is equal to minus infinity, this once again does not satisfy. So if you can cross this, so if you go back and we can update beta value if there is anything. So beta is equal to min of beta value earlier is 3 and v value is 3, which is 3. So this will be returned. So I'll be using green color to the values which returns. So return as 3, return v is 3. So v will be returned to the max value function. So here we will be updating the alpha beta values also, just like how we have done in the previous iteration. So if you can see here, alpha comma beta would be same as minus infinity comma 3, and alpha comma beta values here will be same as minus infinity comma 3. So once we have done this all the 3 iterations, we will be going back to the max value function. So here, so the final return value is 3, so this 3 will go and be placed here. So if you see here, so let's write, so v would be equal to max of, here alpha value is here max of minus infinity, and we got for this whole function, after doing 3 iterations, we got return value as 3. So this would be 3. So the v value here would be 3. And once we computed the v value, we can see here we have to check if it is greater than or equal to beta. So here v, which is equal to 3, greater than or equal to beta, which is equal to, here the beta value, if you remember, our beta is still infinite, because we should not take the beta value inside the ones. So that's why I've written with a different color code. So here the beta value is still infinity in the outer loop, so outer function. So here beta is infinity. So 3 is not greater than or equal to infinity, which you can strike it off, which means that we will not be going into that function, will not be going into that if condition. So if condition is not satisfied, no, the alpha value should be updated. So alpha value would be max of, so alpha is equal to max of v, which is 3. So if you see alpha comma v, so alpha value is minus infinity and v value is 3, which will be equal to 3. So this alpha value we have run one iteration here. So this alpha value will and v value, the latest v value will be running for the second iteration, which means for the action a2. So all these things which we have done is for action a1, being in state A and taking action A1. We have to do all these steps for being in state A and taking action 2, A2. So the values which are going to be migrated are V and alpha values. So the latest V value which we got is 3 and the alpha value is 3. So these two values are going to be moved to the next iteration. So let me go to the next iteration. So if you see here, so the new v value is 3 and alpha value is 3. So once again we will be calling the same way the function. So v is equal to max of, here we used to have v value, so the here v value is 3 and we have to call min miv function. So miv of, so we can take different action. Currently we are going to take from A we are going to take action A2 and this will result in minus infinity and the alpha and beta values. Alpha value is 3 here, so let me just correct this. So alpha value we got from the previous iteration, so we got alpha value as 3 and beta value as infinite. So once again we are going to run all the iterations. So for the first iteration, once again, because once we go to the min value function we have to run everything from the beginning. So v is equal to infinite inside the min value function. So v once again is equal to minimum of, here we are going to have the, so if you go to the min value function we have to have the v value here is infinite, so infinite, and so we should not confuse with the v value here. So here the v value is still infinite and we were going to call the max value function. So mxv of, so here we are going to have r of state C. From C we are going to take the action C1. So if you see from state C we can take C1 and here the alpha value, alpha and beta values. So from here we got the alpha value, so alpha is 3 and beta is infinite. So that's it. So this is what we are going to compute, but we already know this is a terminal state and the terminal state value is, so if you can see here the terminal state value is 2. So from C1 we will get a terminal state value as 2. So minimum of infinite comma 2 will result in v is equal to 2, and this when compared with alpha values, so less than or equal to alpha, here the alpha is 3, but as you can see here 2 is less than 3, so this is satisfied. So this is, the condition is satisfied, which means, so earlier we did not, but here we are able to satisfy this condition, which means, so this condition v less than or equal to alpha has been satisfied. So then return v directly. So it returns the v value. So v value here is 2. So let's write it in green. So return 2. So this is an important step because of this condition check we are able to prune the whole of the rest of the tree. We don't need to further run iterations in the min value function. So all those other iterations we are able to avoid, thereby reduce the computation in alpha beta pruning. So once you return 2, we are going back to here. So we will be having v is equal to max of 3 comma 2, which results in 3. So now, so we are in this max value function. So we have got the v value, which is 3. So we have to check if v is greater than or equal to beta, and also update the alpha value. So if you check v, which is equal to 3, greater than or equal to beta, beta is here infinite, 3 is not greater than or equal to infinite, so you can cancel this. So you can cancel this, and now also update the alpha value. So alpha, new alpha value will be so max of alpha comma, so max of alpha, current alpha value here outside the alpha value is 3. So and the v value is 3. So max of 3 comma 3 is 3, and therefore so the alpha beta values outside. So here I'll use a completely different color to indicate what is alpha beta values outside. So outside alpha comma beta values are 3 as of now, because alpha got, so alpha is now same, so 3 comma infinity. So this is different than the alpha beta values here. So this was inside the min value function, these alpha beta values are outside the function, inside the max value function. So we got alpha beta values, we got the new alpha value, so we can go to the next iteration here. So because we did not complete all the 3 iterations in the max value function, we only completed 2. So now if we go to the third iteration, so let me go to the third iteration. So here, so in the third iteration, so we are going to migrate the values. So values are here the v value. So v is once again 3, which is coming from the previous iteration, and alpha is also once again 3, which also comes from the previous iteration. So once again we run, v is equal to max of the value is 3, and here the min value function. So min value function miv, and r of a comma a3 comma here alpha beta values. So alpha is 3 and beta is infinite. So this is what is the values which we got, and this function is what we are going to expand once again. So when you expand this function, here v is infinite in the min value function. So v is equal to min of so if you go to this v value, so here v is infinite, and max value function. So you can call the max value function, which is mxv. So that will have r of the action here is d. So we are currently in a comma a3 results in d. So the d will be going to take action as d1. So d comma d1, and the alpha value currently is 3, and this is infinite. So and we know this results in a terminal state of 14. So this 14, so when you compute minimum of infinite comma 14, which results in 14. So v value is 14 here, and which is which when you compare with the alpha values, which is 3 here, so less than or equal to 3, which is not satisfied, so this condition fails. So let's use red color. So this is failed, and therefore since it is failed, you can update the beta value. So beta value, if you update here, so beta will be equal to min of beta. Here the beta value is infinite and the v value, so min of beta comma v, so beta is infinite and v value is 3, so which will result in, so here the v value is 14, not 3, so let's so 14, so beta value becomes 14. So now the new alpha beta values, so here let me just indicate using the same color. Alpha comma beta values inside this min value function are 3 comma 14. Okay, so now we go to the next iteration. So in the next iteration we are going to have v values, updated v values as 14, and the beta value is also 14. So v will be equal to min of alpha value, here v value, which is 14, comma, once again we are going to call the mxv function, and here we are going to have r of d comma d2 action, and this results in alpha value is same, beta value has changed to 14. So this results in, so this is a terminal state which has a value 5, so v will be minimum of 14 comma 5 will be equal to 5. So we got a new v value here, and this v value will be checked if it is less than or equal to alpha. So if you see that, so v is equal to 5, which is less than or equal to alpha is equal to here 3, which is not true, so you can cross it off. So you can, if you cross this, you have, so you will not be going into it. Now we can update the beta value. So here beta value will be equal to min of beta, which is earlier 14, and now you have beta v value as 5, which is 5. So beta has changed. So here alpha comma beta values have become 3 comma 5. So we will once again do the one more iteration. So here v and beta values will go back, so one more iteration, so v is equal to 5 and also beta is equal to 5. So just to indicate where we are starting the each iteration, so here we have started, and also we are starting the third iteration of min value function here. So v is equal to 5 and beta equal to 5, so v is equal to min of v is 5 here, and mxv, so let's indicate mxv of, so here r comma r of node d taking d3 action, and here alpha value is 3 and beta value is 5. So if we close this, and this will result in a terminal state as 2. So V will be equal to minimum of 5 comma 2, which is nothing but 2. So V is equal to 2 is less than or equal to alpha is equal to 3. This is satisfying the condition, so we can return 2. So here no need of further updating, you can return 2. So this 2 value is going to the, so final value for returning is 2. So that is going here. But here we have V equal to max of, so V is equal to max of, already we have 3 and now you have having 2. So it is still 3. So although this has returned 2, the final value is still remains 3. So in this way, if you see, the node A will finally reach to the state value as 3. So just to summarize what we have seen here, so we have two functions, mxv max value function and min value function, and your alpha beta search algorithm calls this max value function and min value function alternatively, and attempts to find out the value for the best possible value for state A, state B, state C and state D. Min player attempts to always minimize the value, and max player will always attempt to maximize the value for that state. So since they are competitive, so you will not have the maximum among the terminal state, but based upon what are the best possible values, we will be picking the state values for A, B, C, D. So to summarize, so we have started with mxv function from the node A, and it has called actions A1, A2, this is A2 and A3. So first column is A1, second column is A2 and third column is A3. So this first column A1 resulted in state B, and this state B has 3 actions, B1, B2, B3, and each of those actions resulted in a terminal state 3, 12 and 8, and towards the end we have returned 3. So this 3 got returned to this value MIV, and max value we computed, so we got V value as 3 and alpha got updated to 3. So across these max value functions, V and alpha are getting exchanged, and within the min value functions, beta values are getting changed between iterations. Between iterations, beta values are getting changed, whereas between iterations in the max value function, alpha and V values are getting changed. So we got V equal to 3 and alpha equal to 3 for the second iteration in the max value function, and that resulted into a terminal state 2. And the important thing is, here in the second iteration, once it comes to satisfy this condition which is present in min value function, so it satisfied V less than or equal to alpha. So then it returned V without further going into the other iterations. Thereby we are able to prune these nodes paths like C2 and C3. So we were able to prune the paths C2 and C3 because only the C1 iteration we have done, and it satisfied V less than or equal to alpha. That is what we have tested here. V is equal to 2 less than or equal to alpha, which is 3, and therefore the condition has satisfied and we have returned directly 2. So this has reached to the max value function, so 3 max of 3 comma 2, and we got new V and alpha values. So these new V and alpha values are have been sent to the next iteration in the max value function, and we have once again done for D action A state taking action A3, which resulted in D, capital D, and this D state has 3 actions D1, D2, D3, and each of those resulted in 14, 5, 2, and this 14, 5, 2 resulted finally in a V value as 2, and that resulted in, once again when we apply here 2, so we got final V value as 3, and this 3 value is what is finally being returned to the alpha beta search function. So in this way we are able to, in a competitive multiplayer game, we are able to get the best possible state values for A, B, C, D by pruning some of the nodes and thereby reducing the computation.